Uh, Hi, hello everyone. Thank you very much, the organizers of this conference. Thank you, Bayram. Thank you, Banda, for inviting me on this talk. Can I share my screen?
Sure, Shaheen, could you
Please,
stop
yeah.
sharing, Shaheen? Shaheen Mamadou, can you hear me? Could you stop sharing? Did we lose Shaheen Mamadou?
And now we can do it.
Okay, sure.
Uh, but host has to enable share. Yeah, now we can do it.
Okay.
Okay, so good afternoon, everyone. So my talk will be about some quantum information aspects of problem of time in quantum cosmology. Let me put in a full screen. Okay. This talk is fundamentally based on our work, quantum informational approach to problem of time, foundation of physics. So we will doing a little bit of extension of that work, but the basic core was laid in that paper. So in this talk, it has roughly the four sections. First, I will try to briefly review the problem of time and also the Wheeler-DeWitt equations and different universal models because of the different potential we can have. Then I will go on to use some quantum informational techniques like quantum information and quantum state discrimination to discern or to understand or like to get more insight into this problem of time. Then in conclusion, I will also point out few other future aspects or few other quantum information techniques that we can use to get more insight into this problem. So in quantum cosmology, the problem of time arises because we treat time as an external parameter. And in Wheeler-DeWitt equation, we know that the equation one, we know that H is an Hamiltonian constraint. What would this result is that it will give us a wave function of universe, which is a stationary solution. As you know, that stationary solution, they don't have any dynamics. So this would kind of present as a timeless universe. So that's the whole gist of problem of time, because when we try to naively quantize like put Schrodinger wave equation or Federman equations, we get this sort of problem. Essentially, our quantum states do not evolve traditionally in time in this formalism. But we will see later that there has been different formalisms where we use some intrinsic time, such as the scale factor or other quantities to measure this evolution, measure this change. So we start from a standard FLRW metric, then which we assume to be homogeneous and isotropic. Then we do the mini superspace approximation. That's we integrate over all the position coordinates, and then the Lagrangian inside the integral. We do a legendary transformation, and we arrive at the Hamiltonian. And we do a standard trick of quantizing, all the classical parameter, all the classical quantities or like different operators, and we get the Wheeler-DeWitt equation in the below form, where A is a scale factor and phi is our scalar field. Here we have assumed cosmological constant to be 0, and later we will assume K to be 1, the positive curvature of universe. To make equations even simple, we represent scale factor, change the constant of scale factor to an alpha, which is exponent of an A. Right. So we'll see that in literature, and I forgot to mention, you can see this in classic textbooks about the quantum gravity, how this procedure is done. So in various literature, the scale factor A has been treated as an intrinsic time parameter, and we have seen how this wave function will evolve with respect to it. And And that would mean that it provides a natural framework where we can discuss the quantum state dynamics of universe. Now we will present we will reform our Wheeler-DeWitt equation in this form precisely for simplicity. Here, what we will do, all other factors in this equation except for the second derivatives in scale factor and fields, we will put them as a potential. Now, the form of this potential will describe what kind of universe or what kind of conditions in the universe we are, talking about. So precisely in the textbook of Kefner and also in Zeh, there are more or less like for the simple, like this is a simple approximation for there are uh, three simple kinds of potentials. First is a simple potential where we just assume that a potential has only the alpha dependence and there is no field dependence. The scale factor would only, the quantum dynamics would only depend upon the scale factor, and the quantum state will be determined by the geometry alone. This in the subsequent parts of talk, we will not be talking about this universe in particular. Second important second case is why we take it to be dependent on well dependent on phi, but has a weak dependence on alpha. So this case can be related to the initial inflation when alpha is small. So if alpha is small, we can somehow see that we can use WKB approximation or adiabatic expression. That's in the textbooks how the wave function have been derived for this case. But more importantly, of these simple cases, the most non-trivial case is where there is a non-minimal coupling between alpha and phi. So this will lead to a very interesting dynamics between geometry and a scalar field. And wave function will capture all the dynamics, both of alpha and the scalar field. And so if we to this initial Wheeler-DeWitt equation, we had to do a little bit of redefining the scalar fields in this new variable, which will have both terms of A and phi. So we will arrive at this form of Wheeler-DeWitt equation. So interestingly, this wave function seems like an indefinite oscillators, where we have two harmonic oscillators with opposite sign. So as we will guess, the solutions of it might involve the Hermite polynomials and Gaussian functions. As it has been derived in literature, it's of this form, where Hn and H alpha and Hn are the Hermite polynomials of alpha and phi respectively. And we can see there is a superposition of these states. So there's a summation over all states, and each n state would correspond to the eigenvalue of our reduced Hamiltonian we had here. So this will be important aspect later. There is an discrete values or discrete eigenvalues for this case. So now we will arrive to our main focus of our talk, which is how we can, incorporate quantum information, quantity like quantum Fisher information to get more insight into the problem of time. In quantum information, we usually have quantum Fisher information to measure how sensitive our state is to a specific parameter. In normal quantum mechanics, this parameter is usually the phase of a quantum state, or as time as well. Like we can sometimes measure the sensitivity on the base of time as well. This gives, this goes back to the energy time uncertainty in quantum mechanics. So now if we have a time parameter as an invariant system, like, the initial system where we have taken the proper time t, it's easy to show that the Fisher information will be equal to 0. So what does this mean? So this implies that there is no sensible notion of change of time, or like if we change time, how would the state change? This notion of time in the usual extrinsic time parameter will not be that meaningful. it would appear as if universe is frozen, and and we can see it's clearly the consequence of time representation invariance and the challenges it brings forth in defining our time. However, now as we had earlier defined, we can take alpha to be our intrinsic time. If we go back here, so in this equation, you can like this looks like an a Wheeler-DeWitt equation, but instead of t, we have a second derivative of alpha. But we must be a little careful here, even though it resembles Killian-Gordon equation, but the unitarity is not generally possible. So we have to be a little careful about this. So going back, so as we have seen previously, now phi, the wave function of universe, it had some dependence on this wave function on the time scale, the scale factor. So we know that Fisher information, one of the formulations or definitions of Fisher information is this. And the interesting thing about this, this formula also applies for non-unitary evolution as well. So when we put the function of value of wave function like we obtained in the previous lectures, we see that we arrive at Fisher information, which is clearly non-zero. Thus, this gives an interesting insight that scale factor do influences the change in quantum states. Thus, usually, like when we talk about time, we see there has to be discernible change that can help us detect a change in time. So we see that here, a or the time scale acts like a time-like variable, which can help us, distinguishing the states, quantum states as they evolve. Usually, as earlier mentioned, our quantum state, of universe is very sensitive to the change in it, indicating there is information. Like there is information of if we in the state of universe. Thus, we can use this information to devise a time scale which helps us understand how time moves. And moreover, we can say that at the different values of alpha, the quantum states of universe that are evolved are clearly distinguishable, and thus can help us giving in some meaningful sense of time, although not with problems. It has been the problems of taking intrinsic time have been described in literature. So now to understand another aspect of this of the reparamerization invariant formulation of wave of Wheeler-DeWitt equation and our intrinsic formulation of wave function, we will take an thought experiment and later we will put it in more precise way. Say, suppose, as usually all the thought experiments go, they are always between Alice and Bob. Suppose in our first case, we have the external time t, the physical time t, and our states is a time reparamerization invariance. So suppose Alice prepares a quantum state psi, which is time reparamerization invariant as our universe in Wheeler-DeWitt equation in extrinsic time. And then it does some perturbation, and this perturbation gives us detail of, and this perturbation is depend on the time. So it will, after the perturbation is done, we will have an psi t. Now it will send both of these states to Bob through a quantum channel. And also it will send the associated probabilities related to the, it will also send the eigenbases in which the initial states were prepared. And we send it with these states, the basis set of state information about basis of these states and the probabilities related via classical channel. Now we know due to time reparamerization invariance, Bob cannot distinguish between psi and psi t. That means the information that was decoded in this perturbation, it cannot be, that was coded in this function, cannot be decoded by Bob. Thus, if we have a time representation invariance, Bob cannot have sense of time. He cannot extract information about time. However, if we carry the same experiment with an intrinsic time, like a scale factor, we have seen we have some uh, quantum state at initial value. Not necessarily a is equal to zero, because that will lead to some issues like some initial a. Then state is evolved through some perturbation which depends on a, and it's now a different state psi of a. And as usual, we send both of these states via quantum channel, and also we also send the basis in which they were prepared via classical channel. However, as we can clearly see, as when we were discussing about the Fisher information of these states, Bob can distinguish between these states, between psi prepared at 0 and psi prepared at 8. This means Bob can have information about the perturbation which were dependent on, and thus Bob can extract information about this intrinsic time A. So from above, we get that the laws of physics that are invariant at different chairs of time related will lead to difficulties in defining the unique time, as Hamiltonian cannot distinguish between different this Hamiltonian is the Hamiltonian constraint of the Wheeler-DeWitt equation, not the reduced Hamiltonian that will take data. So to put this wave function in a more concrete basis, we use something that's usually that's called quantum state discrimination in quantum information particles. So quantum state discrimination can be regarded as a game involving two parties, typically Alice and Bob. No surprise there. Alice first prepares a quantum state and sends it to Bob, and then Bob applies appropriate measure. An important assumption in this exchange is that two parties make a parallel arrangement concerning the set of states. That's which eigenstates and their corresponding probabilities where they are parallelly set. So now Bob's goal is to determine among these initial states which state did Alice choose, knowing that he has got these base states from us. The question is now how much one can learn about the state prepared through quantum measurement together with the classical knowledge available from binary information. This is a non-trivial problem in any measurement, as quantum system does not always reveal full information about prepared system. Arbitrary set of quantum states need not be orthogonal, so they are in general not distinguishable from each other. In time representation invariant systems, as they lack quantum Fisher information, it makes difficult to distinguish between quantum states, leading to very high error probabilities. What does this higher error probabilities mean? We will describe. So now Alice sends probabilities pi associated with these quantum states through a classical channel and prepares a quantum state through and Alice has a quantum state among these states which it sends to Bob. Now Bob has to identify which of the states did Alice choose. As we previously said, if the states are not orthogonal, this error will be always something. This error will be always something. It's a inherent property of quantum mechanics. But the whole scheme of quantum state information, quantum state discrimination is that he has to choose such POVMs to minimize those errors. Now, usually, let me go back. So, with each outcome, we associate epsilon I with a positive value operator, which indicates, like, if we have epsilon EI value, that means Alice has chosen this state. So, error in discrimination of non-degenerate set can be minimized by choosing POMs that minimize this probability. So, this the error of judging, like for example, of the state that Alice chose by Bob is given by this formula. The formula calculates the probability that Bob incorrectly identifies a state. You can see, and now interestingly, if in this equation I uh, I put the time reparameterized uh, value reparameterized system, we'll clearly see that the p error will be equal to n minus 1 n if we had first selected n states. But this is a trivial solution. We know like the error equals the probability obtained by random guessing, which implies that Hamiltonian's time representation invariance makes it impossible for Bob to discern any meaningful evolution from the states. We had described this thought experiment and subsequent in our paper. If anyone is interested, they can take a look for the details. So why was this the case? We know that our initial Hamiltonian constraint is a stationary state. Thus, it has an fixed eigenvalue and it has a total degeneracy. And it's because of this degeneracy, total degeneracy, the error when we put in this equation was equal to n times 1 by n, which is equal to the error of choosing among the n random states. Thus, if we have the external parameter t, there is no effective state discrimination, and every state appears to be indistinguishable from others due to degeneracy. However, if we treat this problem using our intrinsic time alpha and put for the energy states here, this state, we put the solutions of our solution. However, you may see that they are little. However, these solutions are little different from this solution. As for this case, I had taken the second case of potential, which is this one. So the solution sorry?
You have 5 minutes.
Yeah, I'm almost done.
Okay.
Okay. So as this is the solution of the wave function. As I had reminded you earlier, this has non-degeneracy. Like there are values of this supposedly analogous energy. So this after we expand this formula, we will have the error in discriminating the states equal to this, which is clearly greater than this, which means there is a non-trivial accuracy which it will be able to discern states, which clearly shows that the reducible Hamiltonian in our case is not merely a constant but governs dynamics and results in a non-degenerate state. This non-degeneracy minimizes the overlap between states and significantly reduces the p error compared to the time representation scenario. Thus, now this is the important piece. There's an effective quantum state discrimination achievable in our case, in contrast to Wheeler-DeWitt case, where such discrimination is not possible due to degeneracy. Thus, in concluding my talk, we can say that the problem of time in quantum cosmology can be addressed using quantum information theory. Not much work has been done the way we have done it, but more like it seems to be promising. More work should be done in scale. And the scale factor provides a promising parameter of time. And also, I forgot to mention, like usually, not just scale factor, sometimes in literature, the scalar period also has been used as an intrinsic time. And interesting research, which future research which we can take us in direction is quantum speed limit. So usually in quantum speed limit usually sets the minimum time of evolution. Thus, if we apply this approach of quantum speed limit for these states, it will tell us a minimum evolution time, which would be interesting. But this is not a trivial problem because usually quantum speed limit is associated with unitary translation. As we shown in our case, it's not generally the case. So problem needs to be so we need to tackle this problem in a very sophisticated manner and to physically get what essentially this quantum speed limit would imply in this another case. Thank you very much for your attention.
Okay. Salman, thank you very much for your nice talk.
Thank you.
We can
Thank
take
you.
some questions.
Sure, sure.
So, are there some questions? Okay, if there are no questions,